All right, so welcome. We're going to talk about substitution when it comes to anti-differentiation or integrals. So the chain rule for derivatives gives us extremely useful technique for finding anti-derivatives. This technique is called the change of variables or substitution. I'm going to pick a different color here. It turns out let's go with orange. Go Miners. All right, so remember how the chain rule, right? So if we had f of g of x and we wanted to find the derivative, this would be the derivative of the outside, leave the inside alone, x, times the derivative of the inside. So here's what we're going to do for our substitution rule. Our substitution rule, we're going to go backwards on this. So now what we're going to do is, okay, this looks crazy. The integral of f dx, what that really should say is the integral of f of x dx is equal to the integral of f of u du divided by du dx. Which is still weird, right? It's still weird, but what we're saying is, hey, look what we have here. We have some function on the outside, f prime. So what we're really going to do is, if we have the antiderivative of the composition of functions, what we're trying to do is this. We're trying to find a value where we just substitute u for our g of x, and we're trying to substitute a du for our g prime of x dx. So that way we could just find the antiderivative of f prime, and it's more of a function that we're going to be used to. So this formula is nuts. This formula is not much better, and this kind of outlines exactly how it relates to our chain rule. The chain rule for derivatives, right? Undoing the chain rule. So what we're going to do is we're going to write u as a function of x, and we think of this as our inside, right? Whatever we would have used as an inside in a chain rule for derivatives, that's what we want to make our u. Now we're going to take the derivative and solve for dx in terms of du. So now we're going to split this fraction that I told you about a month ago you can't split. Now you can split it, all right? So some rules change over time. At antiderivative time, now this becomes an actual fraction and not just an operator of d dx. All right, now this literally means a little bit of u divided by a little bit of x. It's a slope. So we're going to use this expression to substitute the dx. Also, we're going to completely substitute and turn everything that was an x into a u. And, you know, I've talked about it enough. As I say here, sometimes it's easier to understand the process by seeing an example. So let's do an example. Okay, the integral of the quantity 2x plus 5 to the negative 2 dx. Now, if I wanted to do the derivative, which I don't, all right, but naturally this 2x plus 5 looks like it's an inside, right? The quote inside. So what's the derivative of u? The derivative of u is equal to 2 dx, all right, derivative of u. So and it's like we didn't do that section. The derivative of u, we have to have the derivative of x each time. If you prefer, you can write du dx, as we're used to, equals 2, right? If u is 2x plus 5, du dx equals 2, and then we'll multiply both sides by dx to get this equation. All right, so if it's easier for you to write it as a fraction first, du dx, find that, and then multiply by the denominator, you're in the same exact spot. See, but what we want to do is we want to get dx by itself, because I don't have an extra 2 hanging out here. I have an exponent, but we'll worry about that in a little bit. So I don't have an extra 2 hanging out. I just need dx by itself, so I can divide both sides by 2 or multiply 1/2. Okay, so we take this original integral, the integral of 2x plus 5, all to the negative 2 dx. Now 2x plus 5 is the same as u. I leave the negative 2 power, so it's in black. And where the dx was, I replace dx with 1/2 du. Now a 1/2 is just a coefficient. It'll come out in front. U to the negative 2 du. This is an integral in terms of u. It's just another variable. To find the antiderivative, I add 1 to the exponent, divide by that new number. Don't forget the plus c. I simplify, so I have a negative, a 1/2 times a negative, u to the negative 1, so that'll go to the denominator, a negative 1 over 2u plus c. But this problem didn't start with u's, it started with x's. So we always substitute twice, once to start the problem and again to finish it. So in place of u, I reverse my substitution. I'll have negative 1 over 2 times 2x plus 5 plus c. All right, so it's kind of like the chain rule in selecting the inside and the outside, at least in my terminology. All right, so the integral of e to the negative x dx. Our problem here is the inside for an exponential function is the inside the exponent. If u equals negative x, then du dx equals negative 1. So du equals negative 1 dx. But since I don't have a negative 1 hanging out here, I solve for my dx and I'll replace that with a negative 1 du. Now we do the substitution. The antiderivative, or the integral, of e to the u, and then instead of dx, we'll have a negative 1 du. I'm multiplying here, so that negative 1 becomes a coefficient, and if you want to write the 1, you can. Mathematicians are far too lazy to waste time writing a 1. So we have a negative integral of e to the u du, but remember, the antiderivative of e to the u is itself the negative just because it's here at the front of the integral. So negative e to the u plus c. Don't forget to substitute twice, once to make the problem easier or more doable, and here again to finish. So you replace it with a negative x. Substitute twice. Okay, number 3, the integral of x minus 1 all squared times e to the x minus 1 cubed dx. Well, there's a couple of problems here, but having u equal just x minus 1 is not going to help. This x minus 1 cubed is in the exponent of e, so I'm always going to start looking there. I'm going to let u be that entire exponent, just like I did with the previous problem. When I take the derivative, right, derivative of u is 3, leave the x minus 1 alone, subtract 1 from the exponent. So 3 times x minus 1 squared times the derivative of the inside, which is 1 dx, right, whatever dx is. Again, if you need to set it up like this and then multiply by the dx, that's fine. So what do we have? We have an x minus 1 squared, and we have a dx. So we could just simplify here and move only the 1/3 over. I didn't. I decided to use the technique of the book. So I left the x minus 1 squared and the e. The e is now to the u power. Dx, what am I going to replace this dx with? Dx will be 1 over 3 times x minus 1 squared, right? I have to divide by this. Divide by 3 times x minus 1 squared to get dx by itself. These x minus 1 squareds cancel out. And that's what you would see if you stopped here to do the substitution. What I was saying is here, you would have 1/3 du equals x minus 1 squared dx. And then you could substitute these completely, and you'll end up with this integral. You'll have the 1/3 du e to the u. All right, but you can see better these steps, and that's probably why I did it this way the first time. Integral of e to the u is still e to the u. Still have that 1/3 out in front. Don't forget the plus c. Substitute twice, once to start it and once back to end it, and put it in terms of the x variable. All right, so we use exponents frequently as our inside, right, our u substitution. We use things inside parentheses, and of course we're going to use u substitution for things inside of radicals. So let's let u be the radicand, the thing under the radical. U equals 2x plus 3. Du is 2 dx. And solving for dx, I'll divide by 2 and get 1/2 du. Let's see what we'll replace. We still have the integral of 4.1 and the square root, but now it's the square root of u, and I'll have a 1/2 du replacing my dx. All right, so half of 4.1 is 2.05. Those are constants. Let's just bring those out in front so we can focus on the big dogs here, the functions. The integral of u to the, I can't believe I just said that either. The integral of u to the 1/2 du, right? The antiderivative, we add 1 to the exponent, divide by that new exponent. So I'll have a 2.05 coefficient. U to the 1, oh, don't forget the plus c. U to the 1.5, right? We'll call that 1.5. I should have used 3/2, but since we have decimals going on here, I'm going to continue using decimals. So 1 plus 1.5 is 1.5, both in the exponent and in my denominator, plus c. And that 2.05 can be multiplied by c, but that's still just a constant. We would just call it a different constant. 2.05 divided by 1.5, and then reverse our substitution, replace the u with the 2x plus 3 that we started with, and 2.05 divided by a 1.5 times the quantity 2x plus 3 to the 1.5 plus c. The reason I didn't simplify this, I probably should have at least called it 205 over 15 and then factored out, canceled out a 5. But this was going to give me a repeating decimal when I divided, so I just left it as a non-reduced, non-simplified is what I should call it, a non-simplified fraction. That's bad. Bad me. Be better than me. All right. Again, we see a radical, so we're going to let u be the inside, the radicand. Let u be 3x squared minus 1. Then the derivative of u is 6x dx. Solve for dx, we'll get 1 over 6x du. Here we go. What do we keep? We keep the integral of 2x square root, but now we've replaced our 3x squared minus 1 with a u. We've replaced our dx with a 1 over 6x du. Notice here that this x cancels out this x, and so I don't have any x's remaining in the equation. I have a 2, and I have a 1/6, so that makes a 2/6 u to the 1/2 power du. 2/6 simplifies to 1/3. The antiderivative of u to the 1/2, we just did it. That's u to the 3/2 divided by 3/2. But if we're dividing, plus c, I keep forgetting to say plus c. When we divide by a fraction, we multiply by its reciprocal. So we'll have 1/3 times 2/3 u to the 3/2 plus c. Multiply my 1/3 times 2/3 to get 2/9. Reverse my substitution. I'll replace u with 3x squared minus 1 to the 3/2 power, and we still have our constant. All right, this is about as long as I like most videos to go, but since we're calling this a lecture, it'll be a little longer. Most of these problems are straightforward since the dx portion took care of anything we needed, right? We didn't have to manufacture anything. Well, sometimes we have to do our substitution a little differently. We'll do 2 substitutions at the beginning. Nope. We'll do a double substitution at the beginning, but we have to substitute yet again at the end. Okay. That was hard. The integral, just hard to say. It's not actually hard to do. The integral of 2x times the square root of x plus 1 dx. Now, naturally, we want x plus 1, right? It's a natural choice for our inside. If u is x plus 1, then du is equal to dx. But keep in mind, right, that doesn't help us very much. That only gives us the antiderivative of 2x square root of u du. But remember, if u is equal to x plus 1, I can subtract 1 from both sides and find what x is equal to. So if u is x plus 1, x is u minus 1. So now here, right, I did one substitution, all good, but I still have an x hanging out. So I can replace x with u minus 1. I'll have 2 times u minus 1 times u to the 1/2, right, the square root, du. Hey, look at that, all u's and a du. Now we can distribute. I can multiply u to the 1/2 times u and u to the 1/2 times 1. This is u to the first times u to the 1/2. Remember, to multiply two things with the same base, we add the exponent, so that's 1.5, 3/2, because we're using fractions, like real mathematicians. U to the 1/2, right, with a 2 in front of both of those. Here's what's going on. I cannot distribute through the radical, so I can't combine these in any way. But now that the radical is just a rational exponent and a nice simple, it's not a sum, it's a simple variable unto itself, now I can use distribution. And that's why the change of variables is helpful when we have a binomial or higher in the radicand. Double substitution helps us clear it up. All right. So now we have the integral of 2u to the 3/2. We're going to add 1. That's our new exponent. That's our new denominator. Minus 2u to the 1/2 plus 1. That's our new exponent. That's our new denominator. Plus c, so I don't forget. 3/2 plus 1. When we're adding 1 to it, it becomes just add 3 plus 2. And we get 5/2. Keep the denominator. Add the 2 together. Derivatives, you subtract. Numerator minus denominator. Is there a new numerator? So it depends on if you're doing, if you know, you know. That's where I'm going to leave that. Okay. 3/2 plus 1 becomes 5/2. Instead of dividing by the fraction 5/2, I can multiply by the reciprocal. Instead of dividing by the fraction 3/2, I can multiply by the reciprocal. When I'm multiplying, I'll get 4/5. Replace the u with an x plus 1. Right, let's not forget what u started out here. To the 5/2 minus 4/3, multiplying x plus 1 to the 3/2 plus c. This double substitution allowed us to distribute, and that's really what we're focusing on in a problem of this type. All right, that's it for 13.2, substitution. We're going to be using this in the next one too, so be sure to ask your questions if you have them in class.